All right, so yeah, welcome Emanuele and your team from Jump. We're really excited to host you and hear this presentation on your recent work on MSM acceleration using hardware. So yeah, thanks a lot for being here and preparing, and yeah, take it away.
Thank you. Yeah, I assume this is going to be kind of a discussion, so feel free to interrupt anytime. I'm not a super pro of Zoom, sorry, so feel free to just say hey, and then we'll interact. No, because I don't know if I can see all of you. Yeah, this is a joint work between folks at Jump Crypto and Jump Trading. This is kind of the same company, but with two different focuses. And it was pretty interesting for us internally because we were able to bring some of the expertise in hardware into the cryptography world. I figure we can start immediately from the end. So what's happening? What are we talking about? We are talking about larger MSM. So for example, you have 4 million in less than a second and 64 million in about 6 seconds. This was part of the Z-Prize competition. So some of the choices are very specific to that. We built on ArcWorks. We are using the Curve BLS 12377, and we are running on an AWS instance. I thought it would be cool to just show you a demo. So it's not really a demo. I don't know how to call it, but so if you never saw an AWS F1 instance, the thing that you have compared to any other virtual machine is that you have an FPGA. So whether you know or not how to process, how to build, an image for the FPGA, you can take one and use it. For example, you can take ours and just use it. No, so you load this image. So this is Amazon doing some magic. We trust that now the image is deployed on the FPGA. And so now what we want to do is, for example, here we are going to run a test with 2 to the 22. I'll explain the rest later, but so yeah, we can just run it, and yeah, pretty fast is sub-second, right? So now we just computed an MSM for 4 million points in less than a second. I could run it in software. It would take a little bit. We'll see later how long. I just want to show you maybe here you can see the points are stored on the disk for simplicity. We are not generating them. It's about 9 gigabytes. This is for 64 million points. And I just used the first 4 million of those to run this test. And so now let's just run the other test. You're going to see a couple of interesting things. So now it seems stuck, right? So what it's doing is just reading the 9 gigabyte from disk. So it's going to take a while. The second part that we are going to see very soon, hopefully, is that we have to send this point to the FPGA, right? Because the image was fresh. Okay, so now we are sending the points to the FPGA. You have to know that this is also taking some time. So this is just pure bandwidth. We are not doing any computation. We're just transferring. And so now finally we are computing the MSM, and we are going to see the time very soon. Okay, 575. Right. So yeah, I said 566. So I lied a little bit, but not that much. Cool. So yeah, basically today the goal is to explain what's behind this code, what's behind this very short demo. And yeah, let me go back to the slide. So this is going to be our agenda. So the typical question we get asked is, why is Jump Crypto doing this kind of things? I thought a good starting point would be talking about the regular scalar multiplication. You probably know most of that. And then we're going to talk about the multi-scalar multiplication, the FPGA design, and hopefully at the end there is going to be something interesting, whether you are interested in hardware or not, because yeah, there is some surprise in the software world as well. And some of that is really, really recent and new. So you are the first one to know. So Jump is, in a sense, is known to be a trader, maybe an investor for some. And now we are really, really into zero knowledge. So why is that? So first of all, we think, yeah, that zero knowledge, well, let alone blockchain, is going to be one of the key, primitives that we are going to use in the near future. We joke internally that ZK is going to be the new ML. So there is going to be a growth very similar to what we have seen. No? So first of all, cloud providers providing zero knowledge as a service. And anyhow, like it's going to be a big piece of the infrastructure, fast L1 and L2 chain. We are really into bridges, data oracles, and of course the privacy-friendly chains as well. From a hardware perspective, the reason we are thinking about this problem is that I guess similarly to the machine learning, now we can foresee a future where providers offer like proof as a service. It can be a marketplace, for example, but people offering proof and people like creating proofs, requesting proofs. And definitely hardware acceleration, as you will see, helps a lot in that. Again, not dissimilar to how we have seen GPUs coming into the market, TPUs later on to be even more specialized. And we assume there is going to be something more specific, even more for zero knowledge. So we can start from many places. At Jump, we are really good at the infrastructure level, at the low networking. I don't know if you heard, but we are also working on a new Solana validator called FireDancer. So we're really trying to take that at the lowest possible level. And yeah, when we look at the snarks, there are polynomial commitment, IOPs, and then one step below, there are some primitives. There is MSM, multi-scalar multiplication, there is entity, there is going to be hash function, etc. And so this work is specifically targeted to MSM. And yeah, we also have another work on entity. We haven't announced it very publicly because the paper is under review. So we need to wait a little bit before we can start talking about that, but great results also on the entity. If I'm not wrong, you guys are using Halo 2 with a variant using KZG, which means you're probably interested in MSM. Maybe not specifically BLS 377, but yeah, as we will see, many of the things we are talking about, they will apply as well. Cool. So let's start with scalar multiplication. I'm assuming everybody is familiar with the elliptic curve. So these are magic curves where you can define an addition between points. And that practically means that if you have points expressed as coordinates, like for example, X and Y, then you have the X and Y of P, you have the X and Y of Q, and you have some magic formulas that give you back the X and Y of the point P plus Q. So the scalar multiplication, so if you can add 2 points, then you can do this scalar multiplication, meaning you can pretend to do P plus P plus P n times. N is typically a large, for example, 256-bit number, scalar. And so, yeah, we clearly are interested in a way that is a little bit more efficient than doing two to the 156 additions, right? So how do we do that? The typical algorithm is called double and add. The idea is pretty simple. So in my mind, I like to think it going from the right to the left. The best algorithm is probably going from the left to the right, but let's say it doesn't really matter, right? So the idea is that you have an accumulator, a temporary variable that you are constantly doubling. And then you look at the bitwise representation of your scalar. If the bit is 0, you don't do anything. If the bit is 1, you accumulate to your final result, right? So here on the top, you see there is a, if the bit is 1, you add the temporary variable to the final result, conditional add, and then every time you double this initial this variable. I didn't put the initial variable, but clearly R is 0 and T is your point P, otherwise, yeah. Okay, so let's look at an example, no, very simple. The bits are represented from the, so this is the least significant bit to the right, and then we go towards the left, no, as you naturally would expect. So our point T is gonna grow from, P, 2P, 4P, etc. And conditionally, our point R, so first bit is 0, so we don't add anything. Second bit is 1, so we add 2P. Third bit is 1 again, so we add 4P, we get to 6P. And it's easy to see that at the very end, you get NP. So what's the computational cost here? Well, we are doing 1 double for every bit. So in log n double, let's say, or I don't know how to call it, the length, the bit length of the scalar, number of double, and statistically we're going to have 50% 0, 50% 1, so we can safely assume this is going to be more or less half the number of additions. So now we have the basic algorithm. Of course, there is a very wide literature on how to improve upon this basic algorithm. And I just want to go through a couple of things here just to have a common language to talk later. So let's start with the coordinate system. So in the first slide where we saw the points can have coordinate X and Y. And so, yeah, there are formulas. I didn't write the formula. It doesn't really matter to us. But what's interesting about this formula is that they take more or less 3 multiplication and most importantly, 1 inversion. So you have to divide in the field. This is very concerning from a performance point of view because typically an inversion costs 100 multiplication, more or less. No, so yeah, the cost of an inversion is a lot. So now the cost of a single affine addition becomes 100 plus multiplication. So the first approach one can take is to move to projective coordinates. They are typically written in a different way, but essentially you have a Z and the Z accumulates your inversion. So now you don't have any inversion. Clearly you pay in multiplication. Now you need 14 multiplication instead of just 3. And again, the explicit formula are not particularly interesting to us. The last one I wanted to call out is the Jacobian. So the Jacobian, in a sense, they were born because from this observation that we need many more double than adds. So if we can choose what to optimize, maybe we should optimize the double more than the add. And so the double can be done is just 6 multiplication, but you have to pay a price. And now the addition is no longer 14, it's 16, right? But again, as we said before, we are doing many more doubles and roughly half of the add. Any questions so far?
Yeah.
I assume.
Yeah, I don't follow like this. I didn't follow this slide at all. Like I don't understand what you like. What do you mean by x3 and y3 equals? Like what are you dividing there?
Oh yeah, sure. So let me go back a couple of slides. So here the idea is that in this slide you can compute the point R as the sum of P plus Q, right? But practically speaking, your point P and Q are given as 2 coordinates, 2 numbers in a field. And so now you need some formulas to come up with XR and YR. And so these formulas are given explicitly. No? So imagine here you have a bunch of multiplication, addition, etc. between XP and YP and XQ and YQ. Here we call them 1 and 2.
Yeah.
And so you get to the coordinates of the result. Does it make sense?
Yeah. So what do you mean by, what is affine about? Like what is the affine part here?
Yeah, the affine means that every point is just represented with two coordinates, two numbers.
Oh, okay.
The thing is that if you only want two numbers, in the formulas, you're going to have divisions, right? In the explicit, when you try to come up with explicit formula. And so the division is very, very expensive. So you want to try to avoid division. And so you can use some mathematical tricks, for example, using three coordinates. And the idea here is that whatever you have to divide, you're just accumulating into the Z. And so you never divide. Yeah.
Your Z, like, so the Z there is like a helper variable. So X and Y is like
Exactly.
P and Q? Or is each point, like, is P and X, Y, and a Z, where the Z is like a helper?
That's exactly right. Like you need to do it for all the points. So P is going to be in three coordinates, Q is going to be three coordinates, result is going to be three coordinates, right? And when you start, if you start from X and Y, you can have the first one is going to have Z1 equal to 1. But eventually, as you progress in this double and odd computation, the Z is going to be different than 1, so you cannot ignore it.
Okay, so this is like referring to how you like design the like circuit or whatever to compute this. Like that's what you're talking
Yeah, exactly. Yeah, exactly. And this is, by the way, independent from hardware. This is also in software. If you take your favorite library and you're going to look inside. Yeah.
Yeah, like logically the circuit to compute it rather than.
Exactly. Yeah. Exactly. Yeah. And there is a very wide, I mean, this helper variable, let's say the projected coordinates is just one trick. Like I said, there are very many tricks. You like, for example, the Jacobian that I didn't describe at all, but the sense is that you want to optimize the double more than the odd because you are doing more double than odds, right?
Okay, so what do you mean by 16x and 6x? Is it
multiplication? It's the cost in multiplication.
Oh, I see. Okay. So then the projective costs you 14 multiplications, 0 divisions. But is that for the add or for the?
For both.
For both.
Yeah.
Okay. Oh, so why is the Jacobian different than the projective? Like, why is it, or not different, but like, why is the projective have the same cost for both addition and multiplication while the Jacobian has different ones, like intuitively or something? Or is that like very specific reasons?
It's a little bit specific in the sense that they were, in a sense, handcrafted because here you know that you're going to do more double than odd. And so they said, okay, can we find an efficient way to do double instead of treating odd and double the same way?
I see. Okay, so the Jacobian method just treats them as separate.
Yeah, exactly. Yeah, it gets a little bit technical on how they decided to do it. But from our perspective, it doesn't really matter. Like, we're not really concerned about the formulas. It's more just to know that there are different ways, different choices.
No, yeah, that. I think that's clear enough. Thanks.
No problem.
Also, what's the relative cost of the multiplication and then the division? So I think like the projective we do more multiplication, but like 0 divisions. Yeah, that means like very expensive than the multiplication.
Yeah, as a rough number, you can think 100. Like one division costs like 100 multiplication.
I see. That's like the for that FPGA you're saying.
No, this is actually in general, like on a laptop, like on software. If you run a division, it costs like 100. This is a modular arithmetic, so this is modulo p. No, like you are working an integer modulo p, and these integers are typically fairly big. So you cannot really compare the 64 bits multiplication. That's not what we are doing, right?
Yeah, that makes sense.
One thing maybe I potentially want to add here is that have you ever considered some batch of fun add trick which make the division cost amortized over a large batch of of points, so it's using a fine point even can be faster than projective.
Oh yeah.
don't know whether
We're
you
gonna talk
mentioned-
about that later
Okay,
on.
okay.
Yeah, absolutely. Yeah. This is just let's say still background,
Yeah.
right? We haven't started anything yet. So this is a first, let's say, one approach to optimization, or looking what can you do at the curve level. There is also another approach that what can you do at the scalar level, no? And I just want to introduce the NAF because not the adjacent form, because it's pretty important in general in literature, and you may find it independently from our discussion, no? But the idea is that you can represent scalars instead of with just 0 and 1, with 0, 1, and -1. And the reason you can do that is because on an elliptic curve, it's really, really easy. So is as easy as adding a point is subtracting a point, right? Like the opposite of a point is very easy to compute. And so you can do plus p or minus p, and pretty much they have the same cost. And so you can use this trick. So the algorithm to create the NAF is relatively simple. I don't have a very human, easy way to describe, but if you look at it, in an algorithm, it's going to be straightforward. But the idea is that whenever so first of all, let's talk about the definition. No? Non-adjacent means you never want 2, 1 together. You always want a 0 in between a 1, in between 2 1s, right? So you see that in the first line, we have a bunch of 1s, consecutive 1s. In the second line, we never have consecutive 1s or -1. No? There is always a 0 in between, at least 1 0 in between. And so how do you do that? Well, whenever there is 1, 1, 1, you can think of this 1, 2, and 4, right? So what is 1 plus 2 plus 4? Well, it's 8 minus 1. So you can basically replace this string with a 1 in the following bit, and a -1 in the first one with 1. Right? And this pretty much works wherever you are. So I don't want to over convince you, but if you look at the details of this, it's going to be pretty simple. So what does it mean for our scalar multiplication? Well, the number of double, we haven't really touched them, no? Like we still have the same length in bit. But now there is always a 0. And so statistically, it's no longer 50-50, 50-0, 51. Statistically now, only 1/3 of the bits are going to be different than 0, because there is always 1 0. So this is the property of the NAF. Right. And so in this way, we are reducing the amount of addition that we are trying to do. And so this is kind of another trick. There are extensions of this work, of this NAF. They're called sliding windows. So where the numbers are not 0, 1, -1, but it can also be 2, 3, 4, 5, -2, 3, 4, 5, etc. But yeah, I'm not going to talk about that anymore. Okay, are we good on the scalar multiplication? Cool. So now it's time to talk about the multi-scalar multiplication, right? So scalar multiplication is n times 1 point. Here we have n1 p1 plus n2 p2 plus n3 p3. So we have capital N scalar multiplication, right? So yeah, multi-scalar multiplication. And so this is not, or it could be, we will see, but it could be n parallel scalar multiplication, but we also want to add them all. So the very end result is just 1 point, right? So very, very, and capital N, we have already talked about that. It's something pretty large, no? 4 million, 64 million. So it's really, really a massive work of compression down, no? From like we saw in the demo, 9 GB down to 1 single point, a few bytes. So here the idea was to give you a little bit of a sense of why this is a difficult problem. No, we have a lot of random points. We have a lot of random scalars. The point in your case, the case of your interest, the points are essentially, well, I guess both points and scalar, they somehow come from the circuit, right? And the size of the MSM is essentially related to the number of constraints of your circuit. And so if we start from the top, no, we have, like, for example, 64 million points. We need to do, for sure, we don't know how many, but very many point additions. Each point addition we have seen is going to do a lot of field operations. And each field operation is going to be a bunch of multiplication, whether it's on the CPU or in the FPGA. And these are large multiplication. No? So yeah, you can see the scale of the problem is pretty massive. And so it's not hard to imagine that with hardware we can optimize a lot of things along the way. Okay, so I think the first question one may have is, can we use the double and add to do MSM, to do multi-scalar multiplication? No? And so here we are trying to reason why this is probably not the case. So let's say we start with the scalar that are 256 bits, and we start with the number of points 2 to the 26, so very, very, very large. So if we do a single scalar multiplication, we said it's going to be 256 plus half of 256, or plus 1/3 of that. So it's about 200 times 200 point addition. And then we have n, capital N, scalar multiplication to do. So it's 280 n, for example, with NAP. Let's even say that you know a lot more, many more techniques that I didn't explain here, but there are. And so let's even say that you can go down to 200. Right? You still have 200 capital N, but this is still a lot. So the algorithm we are going to show you in the next slide is called the bucket method, and this reduced down to 16, 17 N. So in a sense, the message of this slide is don't even try doing the double and add, because the other algorithm that we are talking about today is going to be at least 1 order of magnitude faster. Right? And so this is really, really important and key to the whole discussion. So in a sense, if you worked on scalar multiplication, you probably know a lot of other techniques, but most of them, the claim is they are essentially meaningless when we talk about large MSM.
Can I just ask one thing? So the 280 times n, it's a lot of computation, but it's parallelizable up to n different processes, right? Like you could do n of
yes.
them in parallel. Okay.
Yeah, 100%. And we will see that also in the MSM, you can do a lot of parallelization, right? So the idea is, yeah, maybe you have a system, you know, with an extreme amount of processor, but for very realistic systems, like with tens or 100 processor, yeah, the bucket method is still winning.
By the way, you will still have an addition chain, like even if you have like maybe like n machines, and you will still have some resulting some addition chain which has some dependency, which makes it hard to use this native approach. So yeah,
that's a great point. So you can run potentially all the n scalar multiplication in parallel, but then you have to add up all the results. No, so you can make sort of a tree, but eventually you have dependencies. No, and yeah, that's so those are less operations, but still It's a significant number of additions. All right, so let's talk about the bucket method now. I just want to mention there is a very good talk on YouTube from the ZK series, highly recommended. I watch it multiple times because every time I watch it, I learn something new. So well, now I implemented everything, so I think I have it pretty clear. But you know, the first time you hear about the bucket method, maybe it's a little bit new, but yeah. So the idea of the bucket method is, so let's pretend that the scalar are really short, no? And then we are gonna see what happens with the longer scalar. But let's pretend, for example, we only have 3-bit scalar, like in this example. So the idea is that we can split the computation in 2 parts. One, we call it bucket accumulation, and the other one, we call it bucket aggregation. And we can do really some magic here. And I think the magic comes in the aggregate. So let's look at the aggregate first. So let's say that all these points are put into the right bucket. At the end, what we have to compute is this S1 plus 2S2 plus 3S3 plus 7S7. So this is kind of a scalar multiplication, MSM, right? But the coefficients are really 1, 2, 3, up to 7. So they are very, very regular, right? And so you can see that you can compute that with a nice trick, which is essentially using just 7 times 2 addition. So 2 addition and a loop long 7. And the way you do it, you start from the bottom. You take an accumulation variable where you put a 7, and your final result where you put the accumulation. Now in the accumulation, you add a 6, and now you add to the result your accumulation. So now in your result, you have 7 plus 7 plus 6. And because you're constantly adding in the accumulation, in the result, you get repeated the top bucket, right? So basically, this trick allows us to compute a slightly complex operation with just 2 addition times the number of buckets that we have. And this is really the key that is dramatically reducing the total cost of the MSM. So how do you arrive to this part of the buckets? Well, you simply go through the points. You look at the scalar of each point, and you treat that as an index in the bucket, and you put the point into the bucket. When I say you put the point into the bucket, I mean practically you add the point to the bucket value. No, so just to go through this example. So P0 as a scalar 2. So bucket 2, we are going to add P0. P1 as scalar 7. So bucket 7, we are going to add P1. Note that the first addition is just setting the point, you know? Like you're not really adding, you're adding to the point 0. So that's very efficient. But now you have point 2, P2. He also has scalar 2, and so it gets added to bucket 2. And so this is a non-trivial addition. And finally, P3 has scalar 6, and so it goes into bucket 6, right? And so, yeah, I guess here you can see, you know, you have 2P0 plus 7P1 plus 2P2 plus 6P3, and here you're just rewriting in this formula the same equation. No? Okay, so with this primitive, we can essentially compute an MSM, no, because this is a linear combination of very many points. But we said we only have very limited limited scalar. No, the scalar must have only C bits. And the reason for that is that we need a bucket for each possible value of the scalar, right? So if we increase the bits, now we have very, very many buckets, right? So how do we do the full 256-bit MSM? Oh, actually, sorry. Let's look maybe at the computation cost, right? So here you have one addition for each point, so an addition. If you have C buckets, 2 to the C buckets, C bit, so 2 to the C buckets, the first addition doesn't count. So you actually have n minus 2 to the C. Now the first addition is for free. Okay. And the second part, we already said we have 2 adds times the number of buckets, which is 2 to the C. Okay. So yeah, now let's look at expanding the full size scalars. So here we pretend in the example, we pretend that the scalar are 6 bits. Okay, you can think 256. And now we said in the example we are splitting over 2. No, so we have three windows. These are called limbs, windows. Internally, we also call them columns because they are in columns. So, okay, so the size of each limb is C, and the total number of windows is W. By the way, this offers also parallelism opportunities because we can process the column completely in parallel if we want. And for each column, what do? Well, we aggregate the column. We accumulate the bucket. This is exactly like in the previous slide, no? Because now it's a fixed amount of bits. And then we have to compute this final result aggregation, let's say. No, we have to shift the result of the proper location. And so looking at the cost, from the previous slide, we have capital N addition minus 2 to the C. We have 2 to the C times 2. And we only have C plus 1 addition. So this is really negligible. No? So remember, C is a very small number. All right. So concretely, let's look at the total cost below. But concretely, let's say N is very big, like 2 to the 20, 2 to the 24, 2 to the 26. C is going to be 16, no, because we want to split 256 bits into column of 16 bits. And so this last part is really, really negligible. In many instances, also the accumulate is kind of negligible, right? Not really, we see, but so really what matters here is the capital N, no? Especially if you have very large instance of the MSM. So for example, in the example below, with C equal to 16, you have 16N. It's gonna, because you have 16 windows. So 16N is the computation, and then you have a million addition for accumulating buckets. Yeah, depending on the size of N, the million addition have an impact high or low. Like, I don't know if you guys follow the Z price at all, but in the Z price, there were multiple competition. There was the FPGA, but there was also the mobile and the WASM. So in software, when you look at WASM, when you look at mobile, and when you look at lower N, like for example, 2 to the 20 or 2 to the 16 or 2 to the 14, then you probably want to do some table and compare the C and compare all these numbers and kind of find the optimal C, that minimizes all the operations. In our case, in the case of FPGA, in the case of large instances, C tends to be less relevant later on. So it's typically either 16 or maybe 20, but not really anything smaller than that. Okay. And Any question on the bucket?
Yeah, would you mind just kind of recapping that, like start to finish, make sure I like follow?
Yes. Let me actually use the next 2 slides that are sort of a recap, and so we'll see, like, if we need to go back, then we'll go back again. So the idea is that we take this scalar has 256 bits, and we split them in limbs, right? So now we have a bunch of computation that can be run even in parallel if we want. The first phase is called the accumulation. So we take the points, we go through all the points, and we put them into the buckets. The second phase is the bucket aggregation. So we aggregate the buckets into a single point. And finally, because these are columns, we need to potentially shift and add up the final result. And yeah, this slide is essentially also that the size of the box is not really in proportion, but it's telling you that the accumulation is very big, the aggregation is smaller, and the final shift is negligible. I just need the space for writing the text. I also wrote it here. So this is the way we wrote it in the paper. You have an MSM initialization where you send the point to the FPGA, for example, or where you can do whatever you need to do. You can pre-process the scalar, for example, to think about this separation in windows. And then you have a phase that is the accumulation phase and a phase that is the aggregation phase. So the first one uses the buckets. So the buckets are kind of an internal state. The second one returns only 1 point. And then you are iterating over the windows. And so you have to just shift the points and aggregate the final result. If we look at the accumulate, you go from 0 to n-1, so you go point by point in a sense. You have to reduce the scalar based on the window, and you have to accumulate, well, you take this is an optimization, I didn't really discuss that, but then you add the point to the bucket. Okay, and then you have the final aggregation, that's the other trick. I need, sorry, to move this, okay. You have the final aggregation, that's the other trick, where you have the accumulator and the final result with the 2 addition times the number of buckets. Okay, so I know this gets a little bit into the details. Do you want me to go back at any point? And
a quick question. So this is just direct Pippenger algorithm, right? Like you just call that a bucket method because, or you think?
Oh yeah, it's Pippenger. Yeah,
yeah.
Sorry,
yeah.
I didn't mention. This is also attributed to Pippenger, so it's also called the Pippenger method. Yes.
Could you just I don't know if you're gonna get to this later, but could you speak about like the parallelizability of this and like across what axis it's parallelized? Because before we could do like all n things in parallel and then add them together. Here it seems like each limb can be done in parallel, but there aren't that many limbs, right? It's like on the order of like 16 or 32 or 64 or something.
Yeah, so you have a few options for parallelization. So the first one is here in line 8. So this is totally parallelizable, no? And it's like we said, probably 16 parallel column. So the other thing you can always do in MSM is split n in 2, right? Like, and so if you have half of the points on one processor, the other half on the other process, right? When you split the points, you in a sense you're doing an extra addition, right? Because at the end you have multiple results and you have to add those together, and then also this part, the way it's written is very sequential. You have to do 2 addition and then iterate. You can sort of do that in parallel, not a lot of parallelism, but you can do a little bit of parallelism there. So there are examples in literature that shows how to do that a little bit in parallel. Again, it's not perfect parallelism in the sense that you lose a tiny little bit of, like every time you split the computation in two, then you have an extra or two addition in the end, right? But in proportion, it's still very effective.
I see. And like in practice, do you split n into like, do you split n? Do you split it into 2, into 4? Like in practice, what is it normally split into for large?
So in software, well, in hardware, as we will see, we use a different style of parallelization. So it's completely different, but and we're going to discuss that. In software, what you see, for example, in Arc or ArcWorks, you're going to see more threads than just the 16 here. Like, for example, I try to run, but it seems to perform decently well. However, there are moments where this explodes, let's say. Now, for example, I run it on a machine that we have with almost 200 processor. And you see that the time, it's not linear, no, but you see a big improvement. But when you run multiple MSM in parallel, then the number of threads explodes, and now the machine performs really poorly. So it's optimized to run one MSM, but if you need to run multiple MSM, then it gets messy. So I think basically this would be better tested on a real world system when you really have a real world use case. That's my point, right? Like, because, for example, in your case, I assume you start an MSM with a batch of blocks, and then while this is finishing, another batch comes. So you start another MSM and then another MSM, right? So it's kind of intermingled in a sense. And so that part needs a little bit more study. That's what I'm trying to say.
Yeah, okay, thank you.
Okay, so there are a couple of tricks that I just want to mention because they are visible in this slide. And if you read the paper, and I think the video I was talking about goes in a little bit more detail. But again, remember the NAF and the fact that we can add and subtract points. So here you can do the same with buckets. You know, you can essentially rewrite the scalar in a way that are positive and negative scalar. It's not really the NAF, it's slightly different. But the idea is that you can add or subtract points from the buckets. So the way I wrote it here is I have the sign. And so this seems a sum, and is actually a plus or minus. All right. This actually has a very big benefit that you halve the number of buckets. So from a memory perspective, with C equals 16, for example, you would have 2 to the 16 buckets if you only add. You have 2 to the 15, so half of that, if you allow add and subtract. So it's actually a pretty good improvement, and we use that in FPGA. It's using Arc. By the way, ArcWorks is well known, but they didn't implement it. So if you want as an exercise to implement it in ArcWorks, that's an opportunity to do it. I didn't look at Halo 2, but I'm pretty sure they do it because it's pretty standard. So the other part is the kind of addition. So I talked about additions here, 2 addition here, and a capital N addition here. Right? If you see here, I call them mixed addition. And the consideration here is that whatever coordinate you choose, you have an extra freedom because the point P, you can probably pre-compute a little bit on that. So oftentimes what happens is that this point P are always affine coordinates, X and Y, or Z equal to 1. And so the formulas that you use here is actually an optimized version of the formula that you use here. And you can save typically a couple of multiplication. So basically, whenever you have a formula for the you choose the coordinates for the buckets. These are full addition on the buckets in the buckets world, but these are accumulating a point which is an affine point, and so you can easily the formula is slightly better, and therefore it's called mixed addition. Make sense? Okay, cool. So this is, in a sense, concludes the overview part about the what is known in literature. No? So how do you do MSM from a theoretical perspective? So now we focus a little bit on very large MSM and FPGA, and I wanted to compare immediately the two algorithms. No? So the idea is that in the init phase, we are going to also initialize the FPGA and send the points to the FPGA. In most of the scheme, including yours probably, the points are fixed, and then you only change the scalar. And so you kind of want to send the point to the FPGA once, and then do very many multi-scalar multiplications, right? So we don't count sending the point to the FPGA as part of the cost for the MSM. That's kind of the reason. This is also called fixed base MSM, right? The MSM is identical to before, and now, so the MSM in a sense runs on the host, on the CPU, no? Like it's a code. In our case, we are running the both accumulation and aggregation on FPGA, but we are running this final part, which is, like we said, negligible run on the host. Again, it depends. Now you can run everything on the FPGA. Originally, we wanted to run the aggregation on the host, but then the Amazon instance was too slow, so we didn't do that. The aggregate is identical. And so there is a novelty here that if you remember before, in the accumulation, there is a novelty. If you remember before, we have a loop on the points. And here we are not looping on the points, but in order, but we are using this scheduler, right? And so that basically this portion of my talk is going to be to try to explain you why we want to schedule things. So let's start at a very high level. What is an FPGA? What is a CPU? Well, you have this mental model of a CPU running a bunch of instructions. So typically, there is parallelism, but one single thread CPU is essentially doing a scalar processing, And we typically think to GPUs. That's not true anymore. You can have SIMD instruction also on a CPU, but we typically think to GPU for doing multiple operation in parallel, same type of operation. On FPGA, the novelty is that you can write your own circuit however you want. And very simplifying, again, I'm not the hardware engineer, so I'm saying things that are a little bit maybe absurd for people that do hardware. But there are two main ways to look at a problem in hardware. One is what we call fully pipeline. So you are trying to write a circuit that progressively go from the left to the right. And the other one is pipelined. So you actually have a loop in the circuit, Like you repeat the same computation over and over. And this is a key point that we are going to discuss in the next few slides, right? So when we look at the overall system, we have the host, the CPU, and the host is going to send over PCIe to the FPGA. And in the initialization phase, we are going to send the points. The points are simply stored in the external memory of the FPGA. So points, we talked about that again before. So it's about 8-9 gigabytes of data. So they don't fit in what is the SRAM of the FPGA, so the internal memory. Internal memory is usually a few megabytes. It's like the cache of a CPU. So you need external memory, which again is still relatively fast. I'm not saying, but it's not as fast as the internal. So this is DDR, but yeah, you have gigabytes of DDR, similarly as you have gigabytes of RAM in a CPU. So then we start the MSM computation. So we send a reduced scalar. We send it into the scheduler. We're going to talk about the scheduler, but essentially the scheduler feed them into the adder, and the adder is responsible to store them, to accumulate it to the bucket. Some point, I wouldn't call it a scheduler. So some points are delayed, so they go into a FIFO. They end up again in XRAM, and eventually they go back to the scheduler, and they finally go into the adder again. Okay, so just some are delayed for a reason that we are going to discuss. So eventually you get the final result into the from the bucket aggregation, and then the result, which is just 1 point, goes back to the host via PCIe. So that's the easy part in a sense. Okay, so this is kind of the overview of what's happening behind the scene of the demo you saw. And now we want to zoom in into the EC adder. And this is where it's important to mention that this is fully pipelined. So the part before is doing a bunch of loops, right, around a bunch of things, and the EC adder is called very many times. Like we cannot have an unlimited amount of this EC adder, but this is EC adder is it's a very large circuit, very, very big, and it's fully pipelined in a sense that we are going to explain. So the idea is that you get 2 points, X, like a bucket, X, Y, Z, T. This is because we use fancy coordinates, and you get a point. You see that the second point is 1 point, so he has less coordinate. This is because we are using mixed addition, so they are kind of different, the bucket and the point. And then this, this is essentially the pipeline. The most important thing are the X, so the multiplications. And at the end, you get 4 coordinates back, so you get the resulting bucket back. And the formulas are essentially what you get from the paper. So this formulas here, processor 1, 2, 3, 4, this is actually from an original paper that described these formulas. So we just took them and implemented in Arduino, right? So they don't look particularly different than what's happening in the paper. So let's talk about why fully pipeline. What does it mean? No. So the idea of a fully pipeline means that you put the input at time 0, T0, and then the input, in a sense, progresses as the time progresses. And you're not going to get the output at the time T1. You're going to get the output several cycles later. For example, let's say 100 cycles later, right? But the nice thing about the FPGA is that at the second cycle, you can already feed a different input. So in a CPU, you're doing a lot of instruction, but in a sense, until you get the result, the CPU is busy. In the FPGA, instead, you can pipeline every single operation at every single cycle. You just have to wait until the very end when you get the result. Okay. So, for example, our FPGA can run at 250 megahertz, and you would say, "Oh, this is really, really small, really little compared to a CPU that runs at gigahertz." But this means we can do an addition every 5 nanoseconds, start a new addition, not complete an addition, no? And let's look at the example here, right? So if I have P0, I have this scalar A0, and so it means that I want to accumulate P0 into the bucket as A0. So at the clock cycle T0, I'm just going to do this, start this operation. If the pipeline length is 100, I have to wait all the way until T99 to get the result back as A0. right? So the total time is going to be 400 milliseconds to get the result. And this is comparable, by the way, with a CPU. So CPU more or less takes the same amount of time. The problem, like we said, the CPU is going to start the next one here. We can start the second one at P1. So we're going to take P1, we are going to take the scalar of P1, and we are going to do the addition, start the addition here, get the result at T100, right? And by the way, when we get the result, the pipe, because it's fully pipeline, you are constantly streaming, no? So when you get the result, it's also the moment where we are sending in a new input. So there is totally no difference, right? So this explains you essentially where an FPGA gets really, really fast. So if we can keep the pipeline busy enough, we can actually do essentially one operation every 5 nanoseconds. The length disappears when we are doing 64 million of these operations, right? Yeah, so this is all nice in practice. There is a caveat. So do you have a question on this? Or shall we talk about the caveat? Or can you spot the caveat? All right, so assuming the pipeline is clear, there is a caveat, and the caveat is what happens if we want to use the same scalar. If we want to use the same scalar, we would have to add the 2 points into the same bucket, but we don't have the result of the first operation until very late, okay? And so we cannot do this operation. So now you know why we need a scheduler, no? So let's say that a 0 and a 1 are the same. So P1, I cannot do it here because I will start with an incorrect result for S0. So I need to just put it aside and delay it until I get the result for S0. After I get the result, now I can feed in P1. All right, it's not a big deal. With so many points, I can just do P2 here, right? So I don't have to introduce a bubble like an empty slot. No? I can feed something else, but somehow I need to be careful and use a scheduler. I cannot just process the point in order. Right? Okay, so this is essentially the core of our paper. Right? Like how do you build a scheduler? And this, when you read the paper, the scheduler is trivial. No, it's just postpone the point, go back, and we study the fact that if you have random scalar, then the probability is on our favor, and so we can actually do it efficiently, right? So the scheduler is nothing particularly complex to implement, but the concept of the scheduler is important because otherwise you don't get the full, you don't get to utilize the pipeline at the full potential. Okay, and so here you can see some numbers. So we'll take a breath for a second. So like I said, more or less, both FPGA and CPU can do an operation every 500 nano. Maybe it's 350, maybe 300, I don't know precisely, it doesn't really matter. But the FPGA can do one add every 5 nanos, right? So, and the CPU, sure, it can parallelize, right? And so the way we approach the problem, how do we compare? This is really apple and oranges. We said, okay, let's try to find the fastest possible compute. Well, not the fastest possible, but a pretty powerful machine, 18 core, 4.8 gigahertz, so overclocked, running GNAR crypto, which is the best library we could find. And that's 24 seconds. On the 18 core with full parallelism, no? And in our case, it's only less than 6 seconds, what we've seen before. Just for comparison, we run it also on the 2.3, and you see there is a 6. So this is 6x slower, right? So it's like comparing on the F1 doesn't really make sense because nobody would use the F1 for its CPU properties. Couple of interesting things here. Well, our implementation is not perfect, right? In particular, the bucket aggregation, so the second part, can be optimized. So if you run theoretically the number, one addition every 5 nanos, you also should get 2 to the 23 less than a second, but we are over a second. So again, if you want to experiment with the FPGA and you're curious, you can. This is a challenge to do 2 to the 23 in less than a second. I don't think it's possible at this frequency to do 2 to the 24, but you know, you can use other techniques. Yeah, and the other part that we want to do is grow bigger, no? So go to 2 to the 30, 2 to the 36, etc. Okay, so if you're still with me in the, let's say, last 5 to 10 minutes, I would like to go back to software and tell you something about software. But before, do you have any question so far or on hardware?
I actually have a question on the previous
sorry, go.
slide. On the previous slide where you showed the caveat, where if you have like conflicting buckets, then you have to delay it. So like in practice, how many buckets? There are only 16 buckets, right? And if your time to run the full pipeline takes like 100 time steps, doesn't that mean that like you have to sit idle for 100 minus 16 time steps?
No, it's 2 to the 16 buckets. Because the buckets are all the possible values of the scalars. Okay. And the scalar are 16 bits, so you have 2 to the 16. Actually, then it's 2 to the 15 because you have plus and minus for the points, but that's a different.
Negative. Okay, and that's a lot larger than 100. How long is how long is the pipeline length in practice? Like, what's the real?
Yeah, it's 100. Yeah, it is. I think
100.
It was 97. Yeah, but I put 100 because it's reasonable.
Okay, so the probability of like a collision should be what it should be low-ish.
Yeah, we have all the number in the paper. Okay. So I think you have two major ways to look at the scheduler. No, one is you set the points aside, and so in a sense you're growing a queue indefinitely, potentially, right? Oh, by the way, the worst case scenario here is when the scalar are all the same. No, if the scalar is all the same, you don't have anything you can do in FPGA. You just have to sit here until you get the result and then pipeline. Right, scalar all the same is the worst case scenario possible. So that's useful to reason about the scheduler. No. But yeah, with the scheduler, essentially, you can put everything in a queue and let the queue grow indefinitely. Or you could have a scheduler that, like I'm suggesting here, where as soon as possible, you use the point that was in the queue. So this, in the first case, with 64 billion, to give you a sense, you're going to have about 200K points in the queue, 200,000. So definitely less than 64 million, right? 200,000. In the second case, where you dequeue immediately, the total length of your queue will never exceed 10. So you can stay in a very, very little amount of space if you need. As a extra point of information, we could only implement the first, so the one that the queue can potentially grow is very large. And so we set a pretty large amount of boundary for the queue. Both in software and hardware, I'm going to talk about software later, we implement that. And we are not able to implement the smart one, let's say, because it gets too slow and then you don't get the benefit of this approach. So that's also an open challenge if you
want. Another question for you. So what do you think is the biggest difference compared with, for example, some previous work like FPGA or some other approaches? Because it seems like in FPGA there is also a pipeline, also use ppanger. It just seems like you use a more complicated scheduler which can handle bucket B size can be 16 bit. Because when we are doing FPGA, it's just we just have like 16 bucket which can only handle 4 bit. the biggest reason is that we use a very simple, just a buffer design without any complicated scheduler for complete. So is that, do you think it's because of this more like better scheduler design, or you think there are some other tricks which makes this faster?
Yeah, so I didn't really discuss, but I think for 377 we are using Edward coordinates.
Oh,
so
yes. Yeah, so
exactly.
yeah, definitely like this this pipeline, like more detailed, like arithmetic, like, but from a high level it seems like pretty similar, like where you have something. Yeah.
Exactly.
Yeah. Okay.
There were compared to the pipe ZK, there were some minor details in the way. I think you guys did also a constant multiplier. The reason mentioned enough, I didn't put a slide, but we use enough in the constant multiplier, so you can get it even a little bit smaller. But that's a detail. No, I think really the thing you want to try to do is get as bigger as the buckets you can, and schedule the pipeline. And to give you another data point, in our case, we have 2 to the 15 buckets. We try to render the same image with 2 to the 16 buckets, right? So to go C equals 17, no? Grow the C. We couldn't at 250 megahertz because the pipeline should be connected to all the SRAM blocks. So it's a lot of connection, and we run out of wires. So on the F1, we were very limited. So at the end of the day, with the limitation of the F1, the only thing you can do is shrink the circuit, increase the bucket, and make sure you go as fast as you can in terms of 250 megahertz. If you could run even more, but we couldn't. So
yeah, that makes sense. So it's because that's the biggest reason why like we are using ASIC for evaluation, because even if we are using like only 2^4 buckets, it's still like we can't increase the frequency and do some other limiting. Okay, so is that concrete, like precise to say, like, you know, like from high level and like the design workflow, it's pretty similar to the MSM part in PEPZK, which is also a, you know, you have some scheduler, you have some addition pipeline, but in more detail, you optimize this scheduler to support larger scale, like more like larger number of buckets. And also like in this like EC adder, like this pipeline version, you use some like, you know, more detailed, more specific, you know, you optimize the, you know, very fine grained, like, you know, in each pipeline, like in each cycle, what you are doing is that because it's more like, you know, we used to do it, that it's more academic work. We don't have really good engineers to heavily optimize some other parts, but the biggest improvement comes from those two parts. Right?
Yeah, exactly, 100%. Yeah.
Okay.
I would say the increase in the frequency is always non-trivial. But it's the thing that gives you more gain, no?
Yeah.
Like the other thing could be having 2 parallel pipeline, but then now you need to feed them, no? And so, it's like having a pipeline long, twice as long, right? So
yeah.
So
what's the biggest difference between yours one and like the one from Anguyama? If I don't know how to read their paper, but what's the biggest difference, do you think? Like if you have ever read their approach, I know like you get more impressive number, but yeah, I just don't know whether you have made some comparison or not.
Anguyama, sorry, which one is it? The one that they published a few months ago?
Yes, I think it's PipeMSM or what, I forgot the name.
Oh yeah. I think honestly, I think it's only because we talked to them, and I think it's very similar to PipeZK in the sense that they were able to go to 250, but on Amazon they couldn't really make it work because it was running over power, a limitation that Amazon imposes.
That makes sense. Okay.
So I think it was just a more complex design overall, like the pipeline was heavier. And then probably also they didn't have so many buckets, kind of similar issue, because if you look at the number, they are 3 to 4 times slower, it seems. They didn't publish this high number, they only published the low one, so it's a little bit hard to compare, but
Okay. That makes sense.
yeah, instead there was a presentation and CESC at the ZK event before, the ZK workshop before, and there was another company that showed very good result, like even better performance, but they are using a different FPGA, so a more professional FPGA, so not the Amazon. Yeah, I think from my perspective, the nice part about results like this in the thinking about the Z price and the achievement is like there is a paper called Gemini. So Gemini is for very large Planck or KZG circuits. Like they did 2 to the 35, no? And we were talking to them, they had to stop because a computation, they ran it on Amazon and it took 1 week. So we are actually trying to work with them and test it, but we expect it to run in a few hours. And the F1 instance only costs $2 an hour, even less, $1.50 for it. So imagine for $10, you have an MSM 2 to the 35. So now also the academic, they can experiment with bigger things, no? Because you cannot really constantly run it for, very many weeks. You also want to submit the paper in in less than 20 months. Yeah, so this was kind of interesting, I think. How are we on time? Do we have time for the software? Software is cool.
Yeah, let's keep going.
Let's go faster. All right, so software. No, most of you are probably partially interested in the hardware, but there is this thing. So if you look at Crypto, Arcworks, they're all using extended Jacobian coordinates, 9 multiplication. No, this is a fact. You go, you look at the code, and you compare. You're going to see extended Jacobian coordinates, 9 multiplication. So it's pretty well known that what we call batch affine, that I'm going to describe in the next slide because I think it's a nice trick, and someone mentioned it before. You can do it 6 to 7. So there is something here. No? So why is everybody using extended Jacobian and not batch affine? And if you search a little bit in this repo, you see a lot of discussion around that. No, so there is a trick here, right? So let's talk about the batch affine. So the idea of the batch affine is that you do the operation as usual, R equal to P plus Q. So you do the classical addition, but now you're not doing 1 point at a time. You're doing on a vector of points, parallel additions, and you want to use affine coordinates, so you save in the number of coordinates, you save memory, and you're gonna want to use this trick. The trick is that the naive way to do it costs T inversion. No, so you have T points, so for each one you have to do an inversion. But there is this batch inversion technique where T inversion, you can transform them in 3 multiplication times the T plus 1 single inversion, right? So instead of T inversion, you have 1 single inversion, but you pay 3 multiplication for each inversion. So if you go back in the affine, now is 3 for the affine plus 3 here, you have 6 multiplication plus 1 inversion. So the inversion also counts, right? And we said before, the inversion is about 100, no? So T equal 100, you would say it's 7 multiplication. This is the easy way. By the way, here I give you the trick. How do you do the batch inversion for the case of 2? No, you do 1 multiplication, and now you have A and B. 1 inversion, and so now you have the inverse of the product. And now you do, if you multiply by B, you get the inverse of A. If you multiply by A, now you have the inverse of B. Right? So 3 multiplication, 1 inversion, and you get 2 inversions. Of course, this is a standard 2T. let's look at the batch affine, right? And now I unveil the trick, right? So you have a batch of length 100, and so you start accumulating the batch. So P0 is going to go in bucket A0, P1 is going to go in bucket SA1, right? And then you close the batch at 100 and you get the results. And so now you start a new batch, right? And so now you should all see the trick here, right? Or the problem. Where is the problem? Well, similarly, so this is the same exact problem that we had in the FPGA. So you want the points in the batch to be distinct, because so the buckets in the batch should be all distinct, no? So the case A1 equal to A0, we cannot put the second addition here because we don't have the result of the first one. The result is going to come here, and so we can only schedule P1 later on in the future. So interestingly enough, a problem that was in hardware, so building the scheduler for hardware gave us a scheduler that can potentially, yes or no, we'll see, work also on batch affine in software, okay? And so here are the results. Yeah, as you can see, this is a MacBook M1 Pro. This is the WSF1, and purely software, no FPGA, not using the FPGA at all. And this is the i9, the other machine we have used before. And you can see pretty much for large MSM, the benefits is pretty high everywhere, right? And so the trick here was just to be able to implement the scheduler and making sure that the scheduler is not consuming CPU and is not actually slowing down the batch affine. And I wanted to show you a couple of things. So this is the PR. So it's hopefully it's going to be merged in GNARC very soon. So I just want to show you. Oh, by the way, it was caught also by Halo 2. So maybe it's going to come also to Halo 2, just FYI. A couple of interesting things. So I didn't even know, but we implemented it for G1, so the classical elliptic curve, but there is also G2. And in G2, they were getting 30% compared to GNARC, even for small MSM, right? Because G2, the computation is more complex, the inversion takes even more, and so now you get even more benefit from the affine. And then this was a paper. So they also worked on Z-Price. They work on the mobile side, and they were leaving this open question for Growth 16. So the scalar are the same for 2 MSM on G1 and G2. So can we do something useful here? And now you see, yes, we can do something useful because now the scheduler can be, so the time for scheduling can be reused on both MSM. So this seems also a pretty cool result. Yeah, that we are just discovering now as we talk about the result. Yeah, cool. So I think this is it. So yeah, we went through the FPGA part. We saw the little demo with the results. Again, we think the key insight, one is the fully pipeline, adder, and then the scheduler for the points. And the scheduler, surprisingly, is the same problem as in software. And so now we probably, hopefully, we have better MSM also in software. Yeah, thank you. If you have any questions.
Awesome. Thank you so much for that presentation. Yeah, if you have some time to stick around, does anyone have questions? You can just jump on the mic.
Have you compared this with some like GPU result, and do you think like it's in terms of the speed up and the energy consumption, it can be better?
Yes and no, in the sense we are pretty confident that the GPU are going to be much better than these numbers on FPGA. For example, in the Z price, they were using a much better GPU than the FPGA. So this group that I was mentioning in the CK workshop at CESC, they are essentially overclocking the FPGA, so making them consume a lot of power. And so they claim that they think they can go as fast as the GPU, but now they consume the same. So which one you use? So for them, the approach is ASICs is going to be the only way to go and to get something better than GPU if we want to compare everything.
Yeah, that's also something like what we are thinking, because we have also very good GPU numbers, and seems like, from the, so is that because, so you build this FPGA, will you also build step to like ASIC to make that more practical? Or because if you stay here, it seems like, people can just use GPU and have a similar number, which, it's a even more general device and needs less configuration. Do you have plans for going to that approach, or you think maybe you manage some FPGA cluster and you still provide this proving as a service? And
from a Jump crypto perspective, as of today, we are not really in the business of providing proof. Like, it's not our main business, So we are going to see what happens with partnerships and opportunities, but in a sense, it doesn't have to be us building the hardware, So we are happy to collaborate on that. We just want to be in the loop and potentially being, showing some good results also in the open source, so that we can connect academia and we'd like to be in the mix. We don't have to be the one building the ASIC. With this said, we had the capabilities, like we build a lot of ASICs internally, so we have both the engineers and the manufacturing capability. So we can also partner with someone and help them scale on that side.
Okay, that makes sense. Is this the fastest MSM implementation in the price? I didn't follow the whole the price, and is this the fastest one, or
They didn't announce yet, so we are hoping to get the result. We hope so, because we think it's pretty good, but well, I cannot say for sure.
Okay.
Do either of you know around concrete numbers of these ends on MSM for GPU, like the state-of-the-art GPU techniques, about how many seconds would it take to do 2 to the 26 MSM?
I think it's around 4 seconds.
4? Okay.
Yes.
So similar. So okay.
Yeah, I think to really gain, you have to go larger. So the larger you go, there's probably something there. And then we see what happens with the Z price, in the sense that everybody's kind of it seems that many people are releasing something to participate in the open, but then they have an internal IP that they are selling essentially. Like I said, we didn't care, so we went all open.
Okay. So will you open source this design and let anyone to use, or still some
100%. Yeah. We will actually cool. Yeah, if you want to see it, we can give you access to the repo. It's just that we are waiting for the Z price announced. We don't know if we can open before the Z price announcement, but cool. If anybody's watching the video later, it's going to be open.
Yeah,
that's really cool that it's in the open and that you guys are presenting it. So thank you for that. Any last questions? All right, I think we'll wrap it up there. Thank you again so much for your time. This was a really, really awesome presentation, and we appreciate your time and your preparation and the work that went into all this. So thanks a lot.
Yeah, thank you guys. Thank you.
All right. Bye, everybody.